All right, so looking on the next page, we're going to investigate a scenario where a critical point can be found by analyzing where the derivative is undefined. So we've kind of talked up to this point where derivatives do not exist, where a derivative is undefined. We've said things like sharp points or cusps, vertical tangents, endpoints. So we have to be aware of where those particular characteristics might be showing up on a graph. For instance, by definition, we said a critical number is where we have a potential max or min. And if you think of an absolute value graph, for instance, notice how there is a minimum on the graph. So this could be or should be classified as a critical point, but the derivative does not exist there because it is a sharp point. So we're going to kind of take a look at this example, not necessarily an absolute value, but this particular function as an example of where a critical point can be found where a derivative is undefined. So if we first analyze our derivative, we'll have to go ahead and use our chain rule. We'll bring down the 2/3, keep the inside, new power negative 1/3, times the derivative of the inside, which would just be 1. And if we add the derivative of 1, that'd just be 0. So cleaning this up, we'll have 2 over 3 times x plus 2 to the positive 1/3 power. Now, typically, we would set this first derivative equal to 0 to help us solve for those critical values, but notice how if you take the denominator and multiply it over to get rid of the fraction, you'd be left with 0 equals 2, which clearly that's not a true statement. So this is basically telling us that there are no horizontal tangents, okay, like perfect maxes or mins where you have those like parabola type shapes. So no horizontal tangents. You don't have a regular parabola, I drew it twice, or an upside down parabola, or even a level spot. Okay, there's none of those going on. But we should analyze here where this derivative is undefined. And notice how since it's a fraction, we have to pay close attention to the bottom. And the specific value of negative 2 would make this derivative undefined. So this should also be classified as a critical point. Wherever the derivative is 0 or undefined, we have to take those both into consideration. So at negative 2, we have a potential max or min. Let's go ahead and analyze our first derivative to see what happens. So domain of negative infinity to negative 2, and negative 2 to infinity. Pick anything negative in here that you want and go ahead and plug it in. For instance, negative 3. So negative 3 plus 2 is negative 1. The cube root of negative 1 is negative 1. Times 3 is negative 3. 2 divided by negative 3 is negative. Pick anything in here, maybe 0. We'd get the cubed root of 2, which is positive, times 3 is positive, 2 divided by positive is positive. So based off of our sign analysis, it looks like we should have a minimum at negative 2 because the derivative changes from negative to positive. But since this negative 2 spot was a critical point from which the derivative was undefined, then this is something interesting going on here, probably like this sharp point from the absolute value. So we're going to go ahead and graph it just to get a good visual of what this would look like. So what I did is I typed in the function on my calculator and I set my window to match that of what's on your paper. So if you hit graph, it kind of looks like this bird shape that you may have drawn when you were younger. But notice how at negative 2, we do have that sharp point where the graph drastically changes direction in which it's traveling. So it looks like that happens at negative 2, 1. And we'll just go ahead and draw in the rough shape of the graph on the other side. So notice how for this type of analysis, when we try to find the critical point, even though setting it to 0 did not really lead us anywhere, we do have to pay close attention to where the derivative might be undefined. Because clearly, based off this graph, we do have a minimum somewhere, even though the equaling to 0 did not lead us to that result. So we have to pay close attention for critical points where the derivative is 0, but also undefined. Let's go ahead and write our descriptions based off of our sign chart here. So f of x is decreasing on negative infinity to negative 2, because derivative is negative. F of x is increasing on -2 to infinity because derivative is positive. And we'll say f of x has a min at x equals -2 because the derivative changes negative to positive. You could also say a statement like f of x does not have a max because we don't change positive to negative, but at least these are the three main conclusions that we can make based off of that table. So what this is leading into is a connection to a second derivative. Like, what if we were to look at that information? What if we were to do a sign chart for the second derivative? And we're going to look at those connections between first derivative, second derivative, and even original function. So up to this point, we know that a first derivative tells us where a function, okay, an original function, f of x, is increasing, decreasing, or has a max or a min. That's what we just did in these past two examples. But what we're going to next start to look at is a second derivative. So what's interesting about a second derivative is it tells us where a function, original function, f of x, is concave up, concave down, or has a point of inflection. So if you think about concavity, we spent some time on this topic last year in pre-calc. Concavity is the curvature of your graph. So if I use a cubic example, notice how initially the cubic function looks like an upside down parabola, but then it kind of switches gears and looks like a regular parabola shape. So if you have this change in curvature where you go from something being concave down to concave up, wherever that curvature changes, that's called a point of inflection. So we're going to take a look at that characteristic a little bit more in this section and even the next. Okay, point of inflection. So since we're adding a second derivative into our analysis, the second derivative is also related to the first derivative. So the second derivative, we'll say f double prime, is the slope of the first derivative. Okay, you're taking the slope of a slope. So since the second derivative is essentially a first derivative, okay, of the first derivative, it has the same properties as the first derivative has with f of x. If I do a quick example, for instance, we'll say if the first derivative is positive, okay, we know the original function is increasing. Okay, we've seen that before. So if I change this, if I go one more derivative, if I say the second derivative is positive, that means the first derivative is increasing. So we have the same connection. It's just a matter of putting an extra prime mark in your functions, but they have the same connections as the first derivative and the original function had that we've been discussing all year.